let's talk about multicollinearity. I know this word is kind of a mouthful, but regardless, let's break it down. Our linear model looks something like this equation, where we have coefficients a0, a1, a2, all the way through ap, that are being multiplied by independent variables x1, x2, so on and so forth through xp. The way we interpret one of these coefficients, so for example A1 is the amount that the output changes if you change x1 by 1, but hold x2, 3, all the way through xp constant. Our model uses an equation like this, and so we try and interpret the coefficients of our model as being the instantaneous rate of change for any one of our features. But what if we can't hold all other variables constant? Well, that's essentially what multicollinearity is. If our features are related to one another, it might not actually be possible to change just one feature while holding all others constant, because if they're related to one another, as you change one of the others might also change, which is specifically when one feature can be predicted very accurately by a linear combination of other features. Now, when this happens, the slopes in our linear regression model don't really mean anything, and we are about to look at an example of this in just a second. Now, this doesn't actually change the predictive capability of our model. The accuracy of our model is unchanged by multicollinearity. Instead, it's the interpretability of the individual coefficients that suffers from multicollinearity. Perfect multicollinearity is a very special edge case, which is when one feature can be written exactly as a linear combination of other features. In such a scenario, our design matrix is not full rank, and so we can't invert x transpose x, and so there isn't a unique solution for our optimal parameter vector theta hat. Now this idea, perfect multicollinearity, you've already explored in great detail. One very common example is when we perform one-hot encoding and have an intercept term. If we don't drop one of our one-hot encoded columns, we can't invert x transpose x, and so there isn't a unique solution for theta hat. But what we are more interested now is in the not perfect multicollinearity case, because that is what is relatively new. And so let's hop back over to the notebook. Okay, so it turns out if we look at the pairwise correlations of the elements in our design matrix, it seems, unsurprisingly, that the field goal attempt feature is very highly correlated with the field goal attempt feature. You can see that their correlation is 0.97. And that makes sense, right? We would expect that the number of shots a player makes and the number of shots a player takes follow a pretty straight linear relationship. And so that is part of the underlying cause of 0 being in the confidence interval for the coefficient on field goal attempts. It's because there is a strong presence of multicollinearity, because this feature can be represented pretty accurately by this feature, and so the slopes themselves don't really mean anything. So in order to prove that, what we will do is fit a new linear regression model that only uses field goal attempts as a feature. And once again, our response will be points. And what we will do is once again look at the multiple r squared value of this model, which is a simple linear regression model because we only have one feature. And you can see that the multiple r squared value is 0.96. So the sort of predictions that we come up with when just using field goal attempts as a feature are almost of the same quality as the predictions that we come up with when using all 5 of these features. So that indicates to us that field goal attempts are indeed actually very valuable for the purposes of predicting average points per game. But that's not enough. We look at the coefficient. In this case, it happens to be 1.29. But once again, we need to think about all of the other possible estimates we could have come up with if our training data looked different. So coming to our rescue once again, and sorry for the spoilers in the notebook, that's kind of just how these are prepared, I can create a estimator function that takes in a shuffled version of our training data, fits a model where field goal attempt is the sole feature, and we also have an intercept term, but field goal attempt is the sole independent variable, and the response is points, and it tells me the coefficient on field goal attempts in this particular resample, and I pass that into my confidence interval function, and it spits back out to me a confidence interval for the coefficient on field goal attempts in the sort of true underlying model that we are assuming exists. And you can see here, 0 is not in this interval. So what happened here? When our only independent variable is field goal attempts, it is quite clear that that feature is very useful for predicting points per game, and it is significantly different than 0. If we instead fit a model with many features, some of which can be predicted quite well by a linear function of others, then the individual coefficients on each of these features don't have much meaning due to the presence of multicollinearity. So this is something you want to watch out for when fitting linear models of your own. Let's quickly summarize some of the ideas that we discussed today. We talked about statistical inference from a more theoretical perspective. We talked about what estimators were, what their bias and variance meant. We also talked about bootstrapping and how we can use it to estimate the sampling distribution of an estimator, and how we can use a bootstrapped sampling distribution to come up with a confidence interval for a true population parameter. We also discussed some of the assumptions that we are making when fitting linear regression models. And we wrapped up by talking about how we can use the bootstrap to come up with confidence intervals for the parameters of our linear regression models, and how multicollinearity can play a role in the interpretability of our model's parameters. Now, this lecture you can think of as being a brief departure from the more machine learning heavy lectures that we've had so far in this class. But I like to think of machine learning as being all about making accurate predictions, while statistics is more about inferring properties of some population. And it's worth mentioning that there's a lot more to machine learning than just making accurate predictions, and there's a lot more to statistics than just inference. In fact, a good data scientist should be well versed in both the predictive and inferential aspect of statistics and machine learning, because you can't really do one without the other. And that's really why we have this lecture here in the first place. Even though I happen to use the word predict quite often in this lecture, we were mostly talking about how to interpret the parameters of our model and what parameters really are. Most of the techniques that we've studied in this class fall under supervised learning in this taxonomy of machine learning, where our training data consisted of an X and a Y, where Ys were sort of our things that we were trying to predict or model. What we will do in the next few lectures is talk a little bit about unsupervised learning, where instead of having both an X and a Y, we just have some set of values X, and we want to learn more about the patterns that exist in the data itself without having the goal of trying to predict some Y value. And so that's what we will do in the next few lectures of this class. That's it for this lecture, though.